In this case, proper time is just 1?
No, in this case, the proper time is, well, the non-proper time, because we're doing it from the muon's point of view. From the muon's point of view, that's how much time it takes. So 6.37 microseconds is equal to 10.01 times the proper time. So 0.63 something. Probably 637.
Uh, 6.36 times 10 to the negative 7?
6.36, okay.
Yeah, 6.6.
Or in microseconds. 0.636.
Microseconds. 637.
All right, so the reason why this is the proper frame is we've already observed it from the point of view of the scientists. People are standing on Earth looking at the muons. We're trying to do this now from the muon's point of view. From the muon's point of view, only 0.636 microseconds has passed. From the muon point of view, this is 0.636. Now how many will be at the bottom? I just erased that other number, so that was, what was the number here?
33.2.
Yeah.
33, okay. So Galilean relativity, 33.2 is our prediction.
What is it?
And whatever this is, I'm waiting for someone to tell me.
Okay, 1.56.
424.405.
In reality, you're not gonna have fractions of a muon.
Oh.
So
424, roughly.
special relativity, we predict 424.4 muons. And the answer, what they actually counted, was 412.
I gotta know, how are scientists in the 40s gonna see muons fast enough that they don't go like,
You see the trails. The trails are there and they linger for just a moment. So if I see a particle coming through, I'll see a trail, I'll see something. Now, what particle it is requires a little bit more sophistication. Probably at that point, you get this giant magnet, or you expose it to a magnetic field or an electric field, which would cause it to curve. As it curves, it's going to, if you know the speed, you can have a good idea what the particle is based upon, well, actually from the radius of its curve when you expose it to a magnetic field or an electric field, you can come up with a mass to charge ratio, which narrows it down quite nicely.
so in this case, or moving to something else, so the time that the muons experience, the 6.37 microseconds, that's just the normal time.
The 6.37 microsecond, that would be Earth time. Now, I hesitate to call it normal time, but that would be, you got some scientists with a stopwatch, that's what he's measuring.
Okay.
Quick finger.
Yeah. The 0.636 microseconds, that's what the muons experience. They age 1/10.
Right, the muons are the ones that move.
Yeah. Questions to hear? All right. Do the muons and the scientists agree on anything?
No.
Well, they will agree on.
They both exist.
True, okay, we'll go with that. 4 things then. There's 4 things, they both exist.
And they're both seeing light at the same time.
Light's still going at the speed of light, regardless for both of them. there's an invariant, and it's a simple derivative, or derivation, but I'm not gonna derive it right now. There's c squared times the time squared minus, actually, times change in time times change in position squared. That's a constant. So t changes, delta x changes, but this combination is true for everyone. The other thing they agree upon is that something is traveling at that speed. They don't agree what's traveling at that speed, but they do agree something is. The scientists say the muon's traveling that fast. What do the muons say is traveling that fast?
Everything else.
I was going to go with the ground. The ground's coming at them at that speed. So if we think about the distance traveled, the scientists say that the muons traveled this far. The muons are saying the ground has traveled, well, they're traveling this fast for that amount of time. The muons are saying that the ground is traveling up at them basically 190 meters. It's that factor of gamma. It's close enough to 10. So there's a difference in the length, and this is known as length contraction. Now I'm going to write it slightly differently than up here that I have for time, because what's the proper frame? In terms of the length of the mountain, what is the proper frame? Or the height of the mountain?
Triangle?
So we got scientists or muons. Who's seen the height of the mountain in the proper frame?
Well, both, I guess.
The scientists. Nobody.
That sounds like you were going for a guess. So we got scientists, nobody, and muons, and both. I think those are the only possible choices.
Wouldn't it depend, pretty much?
It does not depend. It depends on.
Hey, you're looking at an angle, aren't you?
Which one?
No, don't worry about the angle.
Well,
It depends upon the mountains at rest relative to whom?
The observer.
So,
Observer.
Which observer?
Scientist.
Yes.
Because that's what our time's in. Proper time.
Well, proper time is for the muons. This is
Oh.
the scientists.
so,
Oh. Yeah.
But in terms
Yeah.
of length, it's still the scientists have the longer length. But technically, that is the proper length. So in both of these situations, the left-hand side is the scientists, the right-hand side is the muons. These are the muons. It's just officially the mountain, the proper length is what the scientists see, because the mountain is at rest relative to the scientists.
How do we know that muons aren't doing experiments on scientists?
That is quite possible. That some frightfully exquisite and subtle experiments, like the mice do.
they got
Hitchhiker's reference.
really fast brains if they go away every microsecond or so.
But is it a
Yeah.
microsecond to them?
I guess it depends on how fast they're traveling. Now, I guess still microseconds to them would compare to they don't notice, if you're traveling at that speed, if you're on the rocket traveling near the speed of light and you come back and your twin is older, you did not notice anything different. It's not like you suddenly slowed down. It's just everything seemed normal to you. Just back on Earth, things seem to have sped up.
How did they accelerate the muons that quickly?
Some particles come into existence already traveling at that fast. You don't need to accelerate them.
I know that-
Most of it's coming from, I think the sun produces something which decays into muons.
I know that electrons move close to that speed,
But electrons in its normal habitat, electrons as they're going around the nucleus of an atom aren't traveling at that speed.
right, I know we've moved electrons that quickly.
Yeah, we can, because they're nice, small, we get this, the less mass it is, the easier it is to get up to close to those speeds. Because as mass builds, it'd be nice to start with something small. All right, so here's the question.
No.
Taking all this into account. How fast does an 11-foot car need to travel in order to fit into a 10-foot garage?
65 miles an hour. That's gonna cause the foot of the frame to collapse.
Let's assume that the car will actually fit in there without actually having hit anything yet. It will eventually hit something, but you know what? It's a board problem. It's got brakes that will stop it. And once it stops it, it no longer will fit. But we need to, how fast does it need to go in order to fit, at least for just a moment, to fit inside the garage? So when you're given a problem like this, I got two numbers in here. I know that the ratio of distances, just like the ratio, or the ratio of lengths, just like the ratio of times, is this factor of gamma. So from this, we should be able to figure out what gamma is. I know since the car, if I'm sitting from the garage's point of view, the car is coming at me at some huge speed, so the car is going to appear to have shrunk.
But did it really shrink though?
Yes, and we'll get into some of those subtleties, and maybe, at least I'll touch on some of those subtleties. All right, so what is the smallest value gamma can be, or the largest value? All right, and is that the smallest or largest?
That is the smallest?
It is the smallest, because we had a factor of 10 a little while ago. Gamma cannot be less than 1. So I got two numbers here. What do you think gamma is?
1.1.
1.1.
1.1. Those are the two things I'm trying to fit together. I wanted something 11 feet long to look like it, or to actually be 10 feet long. So gamma is 1.1, and so now it's a matter of trying to figure out the speed. That's 1 over the square root of 1 minus beta squared. Now it's a math problem. So I got 1.21 is equal to 1 over 1 minus beta squared.
Where do you get the 1.21?
Squared both sides. And then 1 minus beta squared is equal to 1 over 1.21, just swapping them across the diagonal. 1 minus 1 over 1.21 is equal to beta squared. We're going to flip the sides there. And so beta, ultimately, is the square root of 1 minus 1 over gamma squared. What do we get for beta?
0.417.
So if the car is traveling at 41.7% of the speed of light, it'll fit in the garage.
Interesting.
How long though?
How big an engine do I need to do that?
Very, very, without hitting the wall, very.
Yeah, but say,
I think at that point, if once we can get a car to that kind of speed, that we'll have the engines probably figured out too, so it won't have to be necessarily as big as whatever we have now.
You don't think the engine in my truck will work?
Let me know how it goes if you survive it.
Would it-
All right, so this is from the garage's point of view. The car's coming straight at it. The car shrinks. From the car's point of view, the garage
Gets bigger.
gets smaller. From the car's point of view, the car gets smaller. Sorry, from the car's point of view, the garage gets smaller. So there seems to be an issue there. How can an 11-foot object fit into a 10-foot garage that's traveling at that speed?
About 150 million meters per second, something like that.
130 now?
Yeah, somewhere in that
I just
ballpark.
rounded up to 50%.
All right. The last topic that we're going to cover is a thought experiment, which is going to partially explain how the car can fit inside from the garage's point of view, but not from the car's point of view. I have a train car right here, traveling to the right at some speed v. On top of the car is Lou. Over here is Sue, observing her from the ground. Sue and Lou show up in a number of relativity problems. When the middle of the train is right here, as the train's going by, there's gonna be a flash of light from both sides. Sue is gonna see the flash of light, she'll have a detector over here, and she sees that the flashes of light get to her at the exact same time, so she knows those two flashes of light went off at the exact same time. Lou, on the other hand, says, well, sorry, let's correct that. Inside here, there's another detector. This detector, so I'm gonna call this right and left, so this is the right light and the left light. Or, actually, why don't I stick with standard convention, right light and left light. Sue says the lights go off at the exact same time. Now the car is traveling this way, and so Sue says that the right light is gonna get to the detector first. It's a flash of light goes in all directions, that the light's gonna hit this first because that detector is traveling towards it. Meanwhile, the left light is trying to catch up to it. So if the right gets there first, if right is first to that detector, the detector will show a green light. Now, Lou looks at it and goes, wait a second, the whole car is at rest relative to me. I'm right here. If the lights go off at the exact, if the lights flash at the exact same time, those two lights should get to the center at the exact same time. So, if it's a tie, the detector shows a red light. So they perform the experiment, and then afterwards the car stops and they check to see what light this detector is, and the detector is green. What is wrong with Lou? He says, both the lights, the things that are gonna flash are at rest relative to me. Therefore, if they go off at the same time, that light should reach the detector, which is also at rest relative to me, at the exact same time. What's wrong with Lou's thinking?
Relative to him, not the train car.
Well, I mean, the train car is at rest relative to him.
It's not relative to Sue.
True, but what's wrong with Lou's thinking? Because they are at rest relative to him.
Is Lou moving?
Lou's on the car. Lou's traveling with the car. The entire car is at rest relative to him. Sue is moving that way at some speed.
Is it because the light on the left, the red light is towards the back?
Now, from Lou's point of view, I mean, it's all at rest. There's really no front and back. I will say, Lou is absolutely right. They are all, this whole, the car, the lights, the detector, all of that is at rest relative to Lou. From Lou's point of view, none of that's moving. All right, if I had a detector right here, smack dab in the middle of the room, and I had two flashes of light go off on the sides, if I say that this one gets there first, how could that be?
But I was traveling faster.
Travel the same speed,
If
speed of
The
light.
rotation of the earth.
If
don't complicate
that
it.
side was closer.
No, I said smack dab in the middle. Not worried about the rotation of the earth or anything like that. Let's assume.
The right side is in the front, and if it's going this way, isn't it supposed to hit the light detector first?
Well, that's what Sue claims. Sue was
Yeah,
right.
'cause, I mean,
But from Lou's point of view, it's not traveling that way. From Lou's point of view, this is at rest.
But it doesn't matter. Because,
There is no preferred reference frame. Every reference frame is valid.
but Lou is still moving. Lou is still,
Lou is moving relative to Sue. Sue's moving relative to Lou. Why does Sue win?
Cause Sue said so.
'cause she can observe it?
Well, he can observe it too.
Yeah.
All right, again,
Perpendicular.
lights are gonna go off on the sides of the room. I have a detector in the very middle. The light is gonna travel at the exact same speed. It's gonna go the exact same distance. So if that light gets there first, how is that possible? And it is indeed a very obvious solution once you hear it.
So perpendicular.
What, the light of, the speed of green light moves faster than red light?
No, so
That's a good one.
No.
Good thinking.
through certain mediums, but let's assume I will stipulate
I don't know.
the same speed, same distance.
Lou's smoking and it's causing the light to slow down.
Not an issue with that.
Does it have something to do with the angle of the
Nope,
perpendicular?
not an angle issue, they're gonna travel the same distance.
Alright, let's hear it.
Alright.
Well, I might guess.
Yeah.
Yeah, no.
Alright, let's say that Ronald is halfway between Nick and me, we're both gonna throw a ball to him. We're gonna throw it at the exact same speed, the exact same distance. And I'm gonna say Nick's ball gets there first. How can that ball get to him first?
Is it because the detector's facing the light?
Oh, no,
360 detector.
So y'all both throw it at the same speed and
same speed, same
same,
distance.
same distance away, but his gets there first.
Yep. I thought you were about to say it.
I don't know, I'm just.
The detector can't detect both at once, I don't know.
Wait, say that again?
Detector can't detect both at once?
Not an issue, that's not the issue.
You were close.
How does it tell the difference?
It's a mythical detector.
I'm just, you know, throwing out all, every idea I can think of.
How could Nick get a ball to Ronald before I get a ball to Ronald?
I'm closer.
Same distance.
If he catches yours first, I don't know.
Wow,
And same speed, right? You're throwing the ball
Same
at the same
speed.
speed.
you're making an assumption that is not valid here.
Is Lou not standing in the, no, it's the same distance, right?
Yes,
Yeah, okay.
same distance. The way that Nick's ball gets to Ronald first is that,
His ball is bigger, is that?
nope, not.
Thank you.
Wow, here's the solution. Nick throws first. I never said we throw at the same time. What, only thing that's happening at the same time here is Sue's point of view, they have flash at the same time.
Although.
At Lou's point of view, this goes off first. I never said Lou said it, I said, whenever I talked about Lou talking about that, I said, Lou's thinking if they go off at the same time.
Although your analogy in the room, you did this, which made me think that you flashed them at the same time.
That,
He never said it.
I never said, that was not part of the problem. Just because two things happened at the exact same time from one point of view, doesn't mean they happened at the exact same time from a different point of view. And that is